Hey everyone, welcome back to the channel. I hope you guys are doing extremely well. So finally it's here. Yes, the ultimate dynamic programming playlist. Now you might be thinking, यार इतना क्या hype बना रखा है इस DP series का or what is the hype all about? Now, let me tell you, this is going to be the best. Yes, when I say best, I mean it. I've already delivered one of the best graph playlist, one of the best tree playlist, one of the best tries playlist, one of the best recursion playlist. None of the topics were easy, but I have made videos which will make sure that you build your logics right from the bottom and you go off till the most advanced level of questions that might be asked in an interview. And I promise today, I'm starting the dynamic programming series. And when you end the series, you will be like, yes, this is indeed the best. I know there are a lot of series that exist in the market which are very, very, very good. But trust me, this is going to be on some different level. Point number one, why? The reason is because this series will contain the maximum number of videos which none of the other channels have given. This series will be containing around 60 to 70 videos. Yes, I repeat, 60 to 70 videos. So when you solve 60 to 70 videos on a given pattern, you tend to master a topic. Yes, you do. The second reason is most of the people either teach the tabulation format where they just form tables, they give you some formulas and then they fill up the table. I'm not going to do that way. Now I'm going to do the recursion way, then the tabulation way. Now you might be thinking, okay, this has also been done on the market. Someone has also done the recursion way and then the tabulation way. So what's different in yours? The difference is I'm going to do recursion, I'm going to do tabulation, and after that I'm going to do space optimization, which none of the creators in the market have done. For every problem, I'll be telling you the most optimal solution, which I guarantee no one has ever taught in even the paid courses. Yeah, I might not be able to give you teaching assistance. That is something which I'll not promise. But the content is going to be so crisp and so clear that you will learn completely and you'll have no doubts. So without waiting, let's get started. What is DP? Those who cannot remember the past are condemned to repeat it. This is one of the famous quotes for DP, which is dynamic programming. Yes. Now, when I talk about dynamic programming, there are a couple of ways in which people tend to solve it. One is the tabulation way, while the other one is the memoization way. A lot of people tend to call this memoization. Doesn't matter, as long as you understand, it's okay. Another thing, the series is going to be entirely in English, so it doesn't matter where you are located, you're going to understand each and every word of this series. So when I say tabulation, it means a bottom up dynamic programming. Yes. Now when I say bottom up, it doesn't necessarily means that you're going to start from 0 till n. It can be vice versa also, but yeah, as the name suggests, it's a bottom up dynamic programming. And when I say memoization, it's a top down dynamic programming. Again, when I say top down, it doesn't mean that it is going to be from n to 0. It can be the vice versa also. Depends on your implementation skills. So going forward in every lecture, what I'm going to do is I'm going to teach you the memoization topic. Then I'm going to discuss the time complexity and the space complexity. Once I've done that, I will move to the tabulation. Yes, I'll move to the tabulation and I'll teach you again the time complexity and the space complexity that the tabulation takes. What after tabulation? After that, there is a specific step which most of the creators miss, that is space optimization. What I'm going to do is I'm going to optimize space, yes, in every problem, and that will be our final solution. Generally, in an interview, if you say this, it will work. But if you are going to deliver this, and along with this, I can bet no one is going to ever reject you in an interview. That's my bet. So without actually wasting any time, let's get started with the first lecture, that is again to understand dynamic programming and to understand the entire flow that I'll be teaching. Now there will be a lot of topics which you'll feel like we know this topic, but I'll still recommend you to watch it till the end because there will be certain techniques in every lecture that I'll be telling you. So it might happen like in this lecture I'll be talking to you about Fibonacci, using dynamic programming. Now you might be like, oh, I know Fibonacci, I'm not going to watch it. But trust me, you should watch it till the end. Even if you know, you can watch this on 2x. The reason is because there will be certain techniques that I'll be discussing during Fibonacci, specifically this flow, which is very, very important, how to optimize the space complexity, how to look. So that's why I'll recommend you to watch it till the absolute end. So yeah, let's get started with Fibonacci number. Now the prerequisite for the dynamic programming playlist is you should have done my entire recursion playlist. I repeat, you should have done my entire recursion playlist. It has 19 videos. Even if you don't do 19 videos, I will still recommend you to do the first 10 videos, where the lecture number 6th and the lecture number 7th are of highest importance. Please do the lecture number 6 and the lecture number 7 for sure. So the first problem, Fibonacci number. What's a Fibonacci number? The first Fibonacci number is 0, followed by 1, followed by 1, followed by 2, followed by 3, followed by 5, followed by 8, followed by 13, followed by 21, and so on. Now, if you carefully observe, these are the first two Fibonacci numbers. And when you add them up, yes, when you add them up, you get the next Fibonacci number. Similarly, if you take the next two Fibonacci numbers and you add them up, you get the next Fibonacci number. Correct? So what I can say is the recurrence relation. Again, I have already explained this, so I'll not be explaining the recursion relations in depth in any of the lectures. I'm assuming you are very, very good at recursion. So the recursion relation comes up to be f of n minus 1 plus f of n minus 2 without any doubt. Because whenever I say 5, it says that, okay, for this recursion, this Fibonacci number, you need to know the previous one and the previous to that one. So that's n f of n minus 1 plus f of n minus 2 is what you need to know. Correct? So f of n equal to f of n minus 1, f of n minus 2. Now, if I ask you a very, very simple question, give me the Fibonacci number 4. So assuming I'm doing 0 indexing Fibonacci number, this is the 0th, 1, 2, 3, 4. So this will be the 4th Fibonacci number, which is 3. So I ask you to give me the 4th Fibonacci number. So the moment I ask you to give the 4th Fibonacci number, you will be like, okay, why can't I write a recursion, which you have already done in the recursion lecture. So if you try to write a recursion, the recursion will look something like f of n. And then you'll be like, if n is lesser than equal to 1, you can return n. Or else you can return something as f of n minus 1 plus f of n minus 2. This is the recursion code that you wrote in the recursion classes. Remember, where every guy had couple of options tending out the time complexity to be exponential of this particular recursion. If you don't understand this recursion, please go and watch my recursion playlist. Now, if I try to draw the recursion tree, so the next step, let's try to draw the recursion tree for n equal to 5, where I have been asked to find the 5th Fibonacci number. So f of 5 states I will require f of 4, I will require f of 3. Correct? That is what it states. F of 4 states I'll require f of 3 and I'll require f of 2. Now remember, in the recursion classes, I did tell you, if there is a function call, there is first function call of f of 4, then there is a function call of f of 3. First f of 4 will go, complete itself and come back. Then f of 3 will go, complete itself and come back. You remember, right? So similarly over here, whenever f of 5 calls f of 4 and f of 3, first it goes, completes f of 4, next it completes f of 3. So first it has to complete f of 4. So the call for f of 4 will go at first in the recursion, right? In the recursion, call for this will go, come back. Then the call for this will go and come back. Remember this. So first f of 4 will go. Similarly, when you go to f of 4, f of 3 will be called and f of 2 can wait. Now f of 3 will be like, okay, let's do an f of 2 and let's do an f of 1. Similarly, f of 2 will be like, let's do an f of 1 and let's do an f of 0. Now remember one thing. In the recursion, this is a base case. Whenever you reach f of 1, that's a base case. So you're going to return. So what will you return? You will definitely return 1 because that is what the recursion stated, and it will definitely return 0. So the f of 1 is 1 plus 0 because the previous two, sorry, f of 2 will be 1 plus 0 because the previous two recursion did give you 1 plus 0. So this is going to be, f of 2 is going to be 1 plus 0, which is 1. So this is going to return you 1, correct? Now, whenever you go to f of 1, again base case, so this returns you 1, correct? So when this returns you 1, you get f of 3, which is indeed 1 plus 1 gives you 2. So this is 2. This returns you 2. Now it's a very, very interesting point is over here. We are at f of 4. F of 4 called f of 3, which gave you 2. F of 4 also called f of 2. Now, ideally, what recursion would have done is, it would have gone and created f of 1, then it would have called f of 0, this would have returned 1, this would have returned 0, sum it up, and then it would have returned. So it's a lot of time waste, because is there a need to recompute f of 2? The answer to that is no. Why? Because we have seen f of 2 has been previously computed. Now when I say f of 2, what does that signify? F of 2 signifies second Fibonacci number. So if the second Fibonacci number is 1 over here, it's not going to change over here. The second f of 2 is going to be same. At any instance in the entire program, f of 2 is going to be same. And that is what we call as overlapping subproblems. We solved a problem f of 2 over here, and we again encounter that same problem over here. So that's what we call as overlapping subproblems. Remember this term. Whenever we end up solving same subproblems again, that's when we call it overlapping subproblems. Make sense? So it's a subproblem which has been solved. So will you again go and solve it? There is absolutely no use. There is absolutely no use to solve it. This is where something as memoization jumps in. This is where something as memoization jumps in. What is memoization? We tend to store the value of subproblems. We tend to store the value of subproblems in some map slash table. In some map slash table. Like over here, we are having f of 2. How many parameters are there? How many parameters are there? 1. So if there is one parameter, we can create in 1D array. We can create in 1D array. So I'll come across to that afterwards. How we will create in 1D array and all. We'll come up to that afterwards. But as of now, we don't need to recompute f of 2 because we know the value is 1. So we'll return 1. So f of 4 is 2 plus 1, 3. So we can return f of 4 as 3. Now over here we come to f of 3. Will you compute f of 3? Arey no baba, no. Why? Because f of 3 has been pre-computed. This f of 3 is a sub-problem where we have been asked to find the third Fibonacci number. And we see that the third Fibonacci number has already been figured out. So is there a point of going to f of 2, going to f of 1, going to f of 1, going to f of 0? Is there a necessity? There is no necessity because this has already been computed. This sub-problem has already been solved. So what we do is, we go across and see what's the value stored? 2. So let's return it. So we'll return that value. So over here we get 3. Over here we get 2. So the last and second last will get added up to get 5. So that's how, yes, that's how you're going to solve a normal recursion if you are going to use memoization. Now the question arises, what is memoization? Because I've been talking about memoization till now. What is memoization? That is where the question comes and stands. So over here, you did find out f of 2. So if you carefully see, where are the subproblems? What are the subproblems? There is a sub-problem as f of 5, there is a problem as f of 4, f of 3, f of 2, f of 1, f of 0. So can I say at max the sub-problems are from 0 to 5? Okay, makes sense, 0 to 5. So can I say if I can create an array of 6 size, if I can create an array of 6 size, and I can call that as some DP array. Sounds cool, right? You can call it as Fibo array as well. DP, dynamic programming. So what I did was f of 2 was computed over here. F of 2 was computed over here. What's the value? 1. So I said DP of 2, can you please keep, like initially what I did was, see, initially you'll keep everyone as -1. Initially you can keep everyone as -1. So whenever you go to f of 5, it's -1, you go f of 4 -1, you go f of 3 -1, you go f of 2. So whenever f of 2 is computed, you take this 1 and you store it over here. So please store it. Okay. Now you computed f of 3, that's 2. So please store it. Now the moment you come to f of 2 next time, is that -1? No. Thereby meaning it has some values. It has some values. And from, if it is not -1, from where will that value come? That value would have come from recursion itself. That means you would have solved that sub problem prior to this. Thereby, you can easily pick up this value and you can return it. So that's how it works. Again, there's a call for f of 3. So whenever f of 5 tends to call for f of 3, f of 3 will say, I do have a value 2. So why will I go and call f of 2? Why will I go and call f of 2? So what we do is, we return this value 2 directly. So that's how we do it. And f of 4 was 3, so you can also store that. F of 5 is 5, you can store that. So what I did was, every time a problem was solved, I tend to store that in an array. And whenever the problem is called, I check if that problem has been priorly solved or not. If it has been, I return that value. Otherwise, I do not return that value. That's how I generically do this. So this is the recursion, right? In order to convert this into a dynamic programming solution, generically what we do is, we tend to write something like this. We tend to take a DP array. Now this is the function parameter, right? We'll be carrying an n. We think what is the maximum value of n, because that is the highest sub problem that you'll be solving. Over here it was 5. So I can say I need spaces for n plus 1, because there will be a 0 guy as well. So I require spaces for n plus 1. So I declare a DP array. So remember this. Declare a DP array. That's your first intention. You should always declare a DP array. Once you've done this, what you will do over here is, you remember, this is what you're returning as the value of f of n. This is what you're returning as the value of f of n. So can I say the value of f of n, or the value of this particular sub problem, is this? Thereby, what you can do is, you can just take this and store it where? In this array. Thereby, step 1, remember this. This is step 1. Store it over here. dp of n is equal to, just plunge in a dp of n equal to. That means whatever is computed, whatever is the answer to this sub problem, I'll store it in dp of 1. That's just step 1 to convert a recursion to memoization. What's the step 2? The step 2 is, there is a call made to f of 1, f of n. There is a call made to f of n. You can check base cases. After the base cases, you are calling again sub problems. You're calling sub problems over here, like you're calling sub problems to go and solve them. But over here, you'll not call sub problems. You will first check, is this sub problem being solved previously? So there is a check. If dp of n's value is not equal to -1, I'm saying, is it not equal to -1? Is it having some value stored? If it is having some value stored, I'll be like, why don't you return that value stored? This is step 2. So in order to convert a recursion to a dynamic programming, I implemented kind of 3 steps, where I can say the step 0 is declaring an array considering the size of the sub problems. Like over here there were n sub problems, thereby I declared an array of size n. Step 1, storing the answer which is being computed for every sub problem. Step 2, checking if the sub problem has been previously solved. If it is previously solved, then the value will not be -1. Thereby, I can easily return it. So if you follow these 3 steps, you can convert any recursion to a dynamic programming solution. So the gist of the dynamic programming lies in mastering recursion. If you have mastered recursion, you can easily do dynamic programming. There is absolutely no problem. Like if you have mastered recursion, trust me, DP is going to be not an issue. So what I've done is I've converted this. So generally, in an interview, what you'll be asked is to not use global variables. So what you can do is you can definitely declare an int n. You can take n, and then you can be like dp of n+1 is required. You can memset is to dp of -1 size of dp, and over here what you can write is int, probably int f, and you can keep the int n. And if n is lesser than equal to 1, you can return the n. Over here, step 2 will be concluded, which is dp of n is not equal to -1. That means previously computed, no need to compute. And over here, whatever answer you are getting, like you are usually saying f of n-1 plus f of n-2. So what you'll do is you'll just go over here and say dp of n equal to. So just include 2 steps. But this dp is over here. So generally, I'll recommend you to use vectors. That's how I do it. You can use arrays as well. dp n of -1. And what you can do is you can say C out of f of n, and you can pass on this dp parameter. And over here, you can always take the vector by reference. Okay, by reference you can take it, so that this will be changed on every step. So you can just do it like this, and over here if I give 5, you'll see 5 coming out. Like I'll just run it. Sorry, n+1. I'll do it n+1. So over here, if I just run it, you'll see the Fibonacci number will come out to be 5. So step 1 step, 2 step, declaration, 3 steps. So in this way, you can avoid using global variables, and you can easily write your Fibonacci or DP or any of the DPs. So that's how you do the first step, which is recursion. So I've taught you the first step, which is memoization. Now I have to teach you the time complexity and the space complexity. Let's analyze that as well. So over here, f of 5 called f of 4, f of 4 called f of 3, f of 3 called f of 2, and then 1. 5 steps or n steps. Are these calls going into deep? Are these calls going into deep? No, these are big of 1 calls, like constant calls. So can I say the deeper calls were 5 or n, like f of 5 went on to call f of 3, f of 4, like f of 4 to so I can say f of 5 called 4, 4 to 3, 3 to 2, and to 1. But these calls are constant. So can I say there is a linear pattern? There's a linear pattern, yes. Thereby, I can say the time complexity to be big O of n, which is a linear pattern. What about the space complexity? I can say I'm using a recursion stack space, which is big O of n. So I'm using a recursion stack space because if you've seen my recursion lectures, you'll understand what is stack space. And I'm using a big O of n for array. That's what I'm using. So we have covered up memoization with time complexity as well as space complexity. Now the question arises, how do you convert a recursive solution into a tabulation format? Okay, that's very, very important. How do you convert a recursion into a tabulation? So remember, as a tabulation, what did the name suggest? Bottom up. Okay, so try to go from the base case to the required answer. This is the meaning of the bottom up stuff. Try to go from the base case, like the base case can be anything. And recursion means top down. That means try to go from the base, like try starting whichever answer you require, and then go to the base case and then come back. This is why top down. Over here, you start from the base case and you go to the required answer. Remember a pattern. It's very simple. In recursion, whatever DP array you have used, initialize the same thing. That's the first step. So we used a DP of n+1 in Fibonacci. We initialized that. What are the base cases? Let's go and observe the base cases. Can I say there are a couple of base cases if I carefully see? which states n lesser than equal to 1, given that we require 0th and 1th Fibonacci, can I say dp of like the 0th Fibonacci is 0, and can I say dp of 1 is 1, because that is what the base case exactly states. So you're going to write the exact same thing, dp of 0 equal to 0 and dp of 1 equal to 1, because that is what the base case is. So in order to convert this into tabulation, you'll write this dp of 0 equal to 0, dp of 1 equal to 1 written. What's the next step? The next step is going to be very simple. You again go back and look at the recursion relationship. So the recursion relationship is this: f of n minus 1 plus f of n minus 2. Now can I say this line will be executed when n is lesser than equal to 1, and these lines will be executed when n is 2, n is 3, n is 4, and so on, but nothing before 2. So I know these lines will be executed from 2, correct? So change this to dp, change this to dp, and write it. So I know this will be executed from 2, because the recurrence will never be executed before 2. So from 2 to n is what you write, okay? And you're going to write dp of I, because that is what you wrote over there in recursion, equal to, instead of f of n minus 1, you'll write dp of I minus 1 plus dp of I minus 2. Similar stuff you'll write, just you change it to I and similar stuff. And this is how you can make a tabulation. Interesting, isn't it? Just look at the recurrence and try to convert that into a tabulation, and it becomes easy. What's the time complexity over here? It's big O of n again. What's the space complexity? This time is just a big O of n, no recursion stack space. So it's a better solution that than the recursion or the memoization one, because we are reducing, or we are eliminating the recursion stack space that we were using. Now, how do we eliminate this particular space? I want this to be done in a much better way. So that's when some brain comes in. Like, it's a very standard observation that will help you out. So can I say, in order to find dp of I, what do I require? I require I minus 1. I require I minus 2. Correct? So I require I minus 1 and I require I minus 2, which means the previous and the second previous is what I want. So if I just try to write, like I just give you dots, and I say I is here. Now imagine, you know this is I minus 1 and this is I minus 2 for sure. For this guy, you require this guy and this guy. So just think of in terms of variables. Can I say this as previous as of now? And can I say this as previous, like second previous? I can. In the next step, where will I go? I will go over here, and this will become I minus 1 and this will become I minus 2. Can I say in the next step, I minus 1 will become previous and I minus 2 will become previous 2. And can I do in the similar way in the next step again, where I say I will go here, and this time this will become I minus 1 and this will become I minus 2, which means this becomes previous, this becomes previous 2. Makes absolute sense. Do you see a pattern? Yes, you see. I becoming previous and the previous becoming previous 2. And that's what you all need. You don't need an array, do you? You don't. Okay, so you have seen the pattern, right? So initially previous 2 was the first element and previous 2 was the second element. So let's do the same thing. What I'll do is I'll say, okay, this guy is the previous now, previous 2 rather. This guy is the previous for sure. Now, can I say this is the ith element, which means the cur of I? Can I say instead of I minus 1, I can write previous? Instead of this, I can write previous 2. I can. Similarly, can I say, if I have cur of I equal to previous plus previous 2, in the next because after this, you'll go here, I will increase and I will go to 3. In the next step, this cur I will become someone's previous. So you can be like, okay, but before that, let's say previous 2, for that someone, previous 2 will be previous now. isn't it? If you see, previous to will become previous. So just initialize that, and previous will become karai. Do you agree? Indeed, you have to agree. So in this way, you can keep on going. And right at the end, can I say if you print previous, your answer will be there, because when you will end up, this will go up n plus 1, because the for loop will end at n plus 1. So you will have the previous stored as the Fibonacci number. So in this way, you can optimize the space as well. I have eliminated the space used. I've used just a couple of variables. So if I just use my Sublime text now, what I can do is I can say, okay, previous 2 is 0, previous 1 is 1. I can go on saying I equal to 2, I lesser than equal to n, I plus plus. And over here what I can definitely write is, I can say int car of I is equal to previous plus previous 2, correct? And I can say previous 2 will become previous, and I can say previous will become car of I. And at the end of the day, over here I can definitely do a C out of previous. So if you try to run this, you'll see. So if you try to run this, you'll see this is working absolutely fine. So as simple as it can get. What I've done, I've eliminated the extra space that I was using. Now this boils down into a time complexity of big of n and the space complexity of big of 1. So going forward, in every problem, we will be observing this pattern, where we will be actually using the previous guys and the second previous guys, or something similar to that. So we don't need to always create an array. That's what I wanted to teach you via this Fibonacci number. This is an intuitive solution to this. So that was it for the first lecture. If you need the notes as well as the running codes for C++ as well as Java, if you need both of them, you will find them in the article below. Yes, there is a link of the article. You'll find the C++ as well as the running Java codes for this particular problem. And yes, if you are new to this channel, please do consider subscribing. That is the only request that I will do. And if you did understand this video, please make sure you like this video. And for this DP series particularly, I am starting a trend. After you watch this video, whatever, if you have any doubts, you can put that into the comment section. I will be trying to reply that if it's a unique doubt. And if you have understood, please write this as a trend. Like from now onwards, on every video, at least try to write this small word understood. That is what I will be expecting from you. If you keep on doing this, I will be bringing videos every day till 60. Like for 2 months, I'll bring video every day unless until I'm ill or I'm traveling. I'll make sure I'll bring the videos every day. But this is what I require from you. Like and an understood comment on the video. That is what I'll expect from you. And yeah, please do share this DP playlist among all your friends, because this is going to be the biggest ever playlist. So just before wrapping up this video, just a quick reminder, if you haven't yet checked out SD Sheet, what are you doing, man? The link in the description. Go and check it out, because it's the ultimate resource for interview preparation. So yeah, with this, let's wrap up this video, guys. Let's meet in the next one. Bye bye, take care.
Whenever your heart is broken.